So I'm going to talk a little bit about FreeDV. It's basically a set of ham radio digital voice modes that are optimized more for the high frequency range, like 30 megahertz and under. If you guys are familiar with any like radio terminology at all, and FreeDV basically just has two main components. There's a voice codec, which basically compresses the audio into a bitrate that's low enough that you can transmit over HF in the first place. And also it has a way of modulating and demodulating the audio so that you can actually send it through a radio. And traditionally in the past, it's been used by people just downloading a program onto their computer and having their computer plugged into the radio. I was just going to not use the at all. But do you guys, does it sound better? Okay, so I probably should just use this then. All right. So traditionally, people have just used it with a computer plugged into a radio, but the downside of that, of course, is you basically are just stuck at home. Or if you put it on your laptop, for example, you have to carry your laptop, and that's some of the laptops that are out there are pretty heavy. So why not just make it portable, for example? We actually already have. There's a project called the SM1000. There were a few issues with that. One issue is that the usability of it wasn't really ideal in the first place. For example, there's a little jumper block inside, and the documentation on how to set that jumper block for your particular radio wasn't fully obvious. Not too great. And it was also kind of expensive for what it was. It was about $200 while it was still on sale. And if you're new to FreeDV, you don't really necessarily want to spend $200 on something like this in the first place. So it would be useful to have some cheaper way of getting into like an actual and embedded type device. And we also ran into some limitations with the hardware. So for instance, the STM32 part that uses 1 megabyte of flash, 192K of RAM. And we're actually pretty close, if not hitting that RAM limit entirely. So we can't really add new functionality anymore, especially new FreeDV modes that get developed. And the most important thing that's wrong, especially with the times we're in, supply chain issues. So the STM32F4 that's actually being used in the SM1000, when I made these slides, DigiKey was showing it as next being available in 2059, which is basically a way of saying it's end of life without actually saying it's the end of life. So at this point, it's pretty much time to rethink how a portable FreeDV device should be. And the SM1000 was actually made a while ago, and there have been a few innovations that have come up since then. For instance, newer ham radios that are out there now have network connectivity built in. For example, the ICOM IC705 has Wi-Fi built in. You can tell it to just connect to your Wi-Fi network or have it create an access point itself. And there's various software that you can use to actually communicate with the radio. So you can set your favorite ham radio apps to use a virtual COM port, virtual sound card, and that application basically just goes over Wi-Fi, and instead of having wires connected to the radio like you used to. There have also been a lot of developments in the microcontroller space. So for instance, ESP32, which is what we're going to be talking about today. There's also stuff like the IMRX 1062, which is in the Teensy 4.1. And those have new functionality like higher clock rates and like built-in Wi-Fi and Bluetooth and a whole bunch of other stuff too. So first I needed to set some goals for the device that I wanted to create. First off, and pretty much most important, is to reduce the device cost as much down under 200 as I can. And that's so it makes it more affordable, make it more closer to what an impulse purchase would be, rather than something you'd have to think about and decide whether you really wanted to commit to it. Also wanted to make the ease of use a little bit better, like for instance, maybe make it easier to interface to your radio, possibly even make it so you can just use cables that are already out there instead of having to solder your own cables. Not like the people here probably would be like necessarily opposed to soldering your own cables, but anything to reduce the friction involved in setting this thing up is definitely appreciated. And also make it more easier to set up state-of-the-art functionality. So for instance, it would be nice to have this thing have network connectivity built in, and also features that were added to the PC version of the FreeDV that we haven't been able to add to the SM1000 before. So first off, well, I guess now that I have those goals, needed to figure out how, like, what microcontroller I was going to be using. So the biggest thing that was basically the showstopper is that I needed a microcontroller that had a floating point unit in it. And that's because there's a lot of, if you guys are familiar with C and C++ at all, there's a lot of floats used in the FreeDV code. And if that stuff has to be done in software, that's not a great experience. For instance, I tried running this on a Pi Pico before, and it was encoding and decoding at less than real time, so not great. And also, I'm not really too familiar on the DSP side, so it's way beyond my expertise, unfortunately. It's something I want to learn more about one day, but I didn't really want to have that holding me up and developing this thing. I also needed the ability to interface with the devices that I think would be required. So for instance, I needed to be able to interface with one mic and speaker channel for the radio, one mic and speaker channel for whatever headset or built-in speaker and microphone that I go with, and also whatever buttons, LEDs, etc. That would be needed to interface with this thing. Also, would be nice to support stuff like I2C for whatever other auxiliary chips needed to be put in this thing. And I was looking around, and ESP32 seemed like a pretty obvious choice. Like, it had built-in Wi-Fi, and depending on what ESP32 you go with, Bluetooth or Bluetooth Low Energy. And it also had a clock speed that was comparable to the STM32, about 240 megahertz. And best part, it was about $4 each in pretty small quantities, so it was pretty cheap to experiment on, at least. But then I needed to figure out what ESP32 to go with. And because of that hard limit on needing an FPU, only the original ESP32 and the 32S3 were basically candidates because they both had single precision floating point. And on the Bluetooth side, it would be nice to have full on Bluetooth, but unfortunately, the S3 only has BLE, so not useful for interfacing with a headset. But I figured the headset thing wasn't really a showstopper. The S3 had some advantages in terms of performance, like for instance, it had vector instructions built in, so I figured that might be useful to have, at least to be able to do any optimizations that I needed to do. So I ended up ultimately purchasing a ESP32 S3 dev board from Tindy, Nano ESP32 S3. This was before I realized that Expressive themselves had dev boards, and I could have just done that instead. But I was already on Tindy, and I was just browsing, and I saw that there, and I figured I'd just go with it. The seller who was selling the Nano ESP32 S3 had an option for extra RAM and extra flash as well, and I figured I'd just get that just for the hell of it. I'm thinking that I may or may not end up needing that extra RAM and flash, and it turns out that was pretty useful to have, especially for the built-in Wi-Fi functionality of, for instance, the ICOM IC705. Dealing with the protocol for that actually required a fair bit of that extra RAM. So, and then I also, just for completeness, I tried the standard ESP32, and I was able to get the FreeDV code running on it, but it was just barely slower than real time. 180 milliseconds to encode 160 milliseconds of audio, for example. But I imagine, since it's so close to being real time, if I gave it a little bit more time, it could potentially run properly on the standard ESP32 as well. And there's also the possibility that it was something in my build environment. I just need to sit down and actually play with that again. So now that I've decided on the ESP32 S3, needed to figure out how to get sound into this thing. And as you guys may be familiar, some ESP32s have built-in ADC and DAC. It only has a 12-bit resolution, but that actually may very well have been enough for FreeDV. The badge that I've been working on for Supercon, for example, I've been able to get a triangle wave to output on with only 4-bit audio. So it's very possible 12-bit may have been okay. The S3 also doesn't have a DAC. It only has an ADC. So I would have needed another component anyway to go back to analog. So I was looking around, and there was actually a fair number of audio codec chips out there that basically did the that basically served as an ADC and DAC. And one that I kept seeing pop up a lot was Texas Instruments TLV320. It turns out it's pretty commonly used in a lot of stuff. Like it's geared towards phones, for example, and at least one ham radio, the Elecraft KX3, actually does use a TLV320 internally. It's also about $8 to $10 each in small quantities as of the time I made these slides, so it's pretty reasonably priced as well. So before I decided to commit to the TLV320, I needed to figure out whether this would work in the first place. So the obvious choice would be to buy an EVM. The TLV320 EVM from Texas Instruments is $300, which is way more money than I really wanted to spend on a part that was only $10 and that may not have worked for this application. So I figured I'd just jump in headfirst and build my own effectively evaluation board for this. I don't really have much experience in like PCB design and like the hardware side, but I figured it's a low stakes. I'd have some fun, gain some experience for nothing else. And these days, SMD assembly and PCB fabrication is pretty cheap. A JLC PCB, for example, only charges the part cost and a fee per part for what they call extended components, which admittedly is a fair number of their parts library, but I still thought it was pretty reasonable. So I ended up designing something in KiCad. And the first pass actually I thought it turned out pretty well, but I did find bugs in the hardware as soon as I submitted the Gerber files to JLC PCB, which is always how that turns out. But the board looked pretty good quality enough. And so I figured it was time to work on the software, which led to I2SL, as what I call it anyway. Ended up, a lot of the quick start stuff that I was seeing online actually was basically assuming 44.1 or 48 kilohertz effectively, because that's what most hardware designers like using it with. But the FreeDV code actually uses 8 kilohertz internally, and I didn't really want to do software downscaling, so I wanted to be able to run the TLV320 to at 8 kilohertz. So since there wasn't really quick start stuff for that already, I basically had to spend a very long time with the TI documentation and the helper tools and days and days of debugging to eventually get something that was actually outputting and inputting audio somewhat. But I found that it was only about 3/4 working. One of the audio channels, so the way that it was going was the TLV320 part that I was using had effectively two stereo channels, and I was basically multiplexing that into four mono channels effectively. So what basically was happening was one of those mono channels wasn't really working all that great, and I was probing around a little bit and doing some debugging, and it sounded like it was there. Like I was only really hearing noise, and it looked suspiciously like pulses, like the kind of pulses you'd see on AC. And at the time, I was thinking that software bugs wouldn't necessarily cause that to happen. Like the audio, assuming it was configured right on the I2C interface, would have been either all working or not working at all. So banged my head for a little bit, and I just figured, I kind of just assumed at that point that it was an EMI issue. So I bit the bullet, respun the board to mitigate that, as well as fix some of the other issues that I found when I first submitted the board. So that led to version 0.2. And basically, you see it on the left. The difference between that and 0.1, I added some mounting holes, fully rerouted the TLV320, so all the traces to and from it to try to shorten them, and to try to shield the sensitive ones as much as possible, basically trying to do what's effectively a Faraday cage around those traces. And I also did a little bit of component tuning as well, mainly for the LEDs and the pull-ups and that sort of thing. And then after doing all this, I got the 0.2 board. Looked pretty nice. The noise was still there though, so kind of freaked me out because I was thinking like I said, I didn't have much experience in this whole thing, so very possible I made the same mistake that I made the first time. So I was kind of freaking out during that time. And then I found out that the TLV320 itself, there are some I2C commands you can send to it that basically have some loopback modes built in that bypass the microcontroller. So, for instance, you can send audio into the TLV320, and it basically does the ADC and then immediately does DAC on that audio back out to your headphones, for example. So I ended up testing with that and found out everything was working fine. Like I actually had configured it correctly on the I2C side. So it turned out it was a firmware bug after all. So ended up investigating more, and eventually found that firmware bugs. It was a kind of like a buffer issue, common C bug. Which, funny enough, it's kind of like why a lot of people are really starting to get into the Rust language now, because it makes it a lot harder to make those types of mistakes. But separate subject. So I figured I got something mostly working now. So I figured I'd bump up the difficulty. So first off, I integrated the ESP32 itself onto the board instead of just relying on that nano ESP32 that I was using before. And the upside of that was it left more room for stuff like battery gauge and a fuel gauge, so I could actually run this thing on batteries. And it also made the whole board stack a little bit thinner, so could actually shrink the size overall as well. So I ended up with a couple new board revisions during that time. The photo on there that you see on the screen right now is 0.4. And the only real difference between the two is 0.3 and 0.4. I basically was trying to do some cost optimization. So I removed a lot of the pull-ups that weren't necessary and just relied on the ESP32 internally, for example. And I also added some thermistors to disable the battery charging when it gets too hot or too cold, because it turns out that that's really important for lithium batteries. See a lot of videos online of batteries just blowing up and like catching on fire, so that's not really something I wanted to have happen with this thing. So I actually have this right now if you want to see it after, but I learned a few lessons from this experience. The hardware development is definitely more difficult than just working in software, especially if you're like me and don't really have much experience and haven't been formally trained in that sort of thing. But mainly there's a lot of moving parts involved. Whatever you do on the hardware side, you're basically going to have to make sure you're doing the same thing on the software side. So you change where GPIO goes, you have to update the software to have the GPIO that you're using be correct. Hardware vendors don't exactly make their products easy to use outside of the common use cases as well, but that could just be a function of me not having enough experience yet to properly deal with that. But in any case, hardware development has gotten more accessible for especially like someone like me who maybe is only doing this as a hobby thing and not really trying to sell this, at least yet anyway. Like 5 or 10 years ago, I would have had to contract out with some other board design house and maybe somewhere more local, and I'd have to get a lot more boards made, spend a lot more money on it. And these days we can just upload the board stuff online, and a couple weeks later you get fully assembled boards, or just the PCBs, and you can solder it yourself to save a little bit of money. Also, definitely should read the data sheets. For instance, I found out later, I don't know if you can see this all that well, but I found out later that I was using the wrong GPIOs for the thermistor. I actually wired it on the PCB to a pin that does not get controlled by the ADC at all. So I had to bodge a wire to a pin that actually did support ADC. So definitely double check some things on that for sure. And also, if I had spent more time basically debugging the software, actually ruling out a software issue for sure, then I probably could have delayed doing a new board spin for a while. But since I jumped the gun and figured it was an EMI issue, I probably spun a new board more quickly than I than I probably needed to, where I could have just spent that time working on adding functionality, for example. And so that's basically it for the slides. I don't know how much time I have left for questions or whatever. But if I'm going to be here for the rest of the day, you can go ahead and my email is up there. I also have a personal GitHub as well, github.com/tmiw. And if you're interested in the project, it's called EasyDV, github.com/tmiw/EasyDV, and I welcome pull requests as well. So thank you guys.